In the heart of the 20th century, a battle of minds was brewing. Two of the greatest physicists of all time, Albert Einstein and Niels Bohr, were locked in a series of public debates. These weren't just debates, they were about the very nature of reality itself, the core of quantum mechanics. The stage was set at the Solvay Conference in 1927, and the echoes of their discussions still resonate in the corridors of science. The crux of their disagreement? Bohr's Copenhagen interpretation of quantum mechanics. In simple terms, it suggests that particles exist in all possible states until they are observed or measured. Once observed, they choose one position or state. This interpretation also emphasizes that we can only talk about the probabilities of different outcomes, not certainties. It's like each particle is saying, I could be here or there, but you won't know until you look. Einstein challenged Bohr's belief in complementarity, questioning if it truly explained nature. Despite their intellectual tug-of-war, the two friends maintained a lifelong friendship. They admired each other and learned from each other. This is the story of the Bohr-Einstein debates, a tale of friendship, respect, and the relentless pursuit of understanding the mysteries of the universe. In the early 20th century, Max Planck made the groundbreaking discovery that energy is quantized, meaning it comes in discrete packets, not continuous waves. This revolutionary idea marked the birth of quantum mechanics. Albert Einstein was one of the first to realize the profound implications of Planck's discovery. In 1905, he proposed that light itself is made up of these energy packets, which he called light quanta, or photons. This was a radical departure from the classical wave theory of light and suggested a duality. Light could behave both as a particle and a wave. However, not everyone was on board with this idea, and Niels Bohr was one of those who disagreed. He didn't like the arbitrariness it introduced into the equations of physics. To him, the beauty of physics was in its mathematical elegance and determinism, and the photon concept seemed to undermine that. This disagreement between Einstein and Bohr sparked a series of debates, known as the Bohr-Einstein debates, which were some of the most famous intellectual sparring matches in the history of science. Despite Bohr's resistance, the concept of the photon started to become more widely accepted. In 1922, Arthur Compton performed an experiment showing that light could indeed behave like a particle, lending strong support to Einstein's photon theory. Bohr, however, wasn't easily swayed. He collaborated with Hans Kramers and John C. Slater to develop the BKS theory in 1924, which was an attempt to explain the behavior of light without invoking photons. But in 1925, the Botha-Geiger experiment showed that the BKS theory was incorrect, and Einstein's photon hypothesis was proven correct. This marked a turning point in our understanding of light and laid the foundation for the modern field of quantum mechanics. In the mid-1920s, the world of physics was undergoing a seismic shift, with Albert Einstein and Niels Bohr at the helm. This period, known as the quantum revolution, was marked by intense debates and paradigm-shattering ideas. The first shockwave for Einstein came with Werner Heisenberg's 1925 paper on the quantum theoretical reinterpretation of kinematical and mechanical relationships, where he reinterpreted the old quantum theory using matrix-like operators, effectively removing the Newtonian concepts of space and time from the underlying reality. This was a radical departure from classical physics and set the stage for the development of quantum mechanics. Around the same time, Erwin Schrödinger developed a wave mechanics formulation of quantum theory, leading to the now famous Schrödinger equation. When Schrödinger shared his equation with Einstein, Einstein hailed it as a work of true genius. However, the quantum revolution was far from over. In 1926, Max Born, in collaboration with Heisenberg, proposed that mechanics should be understood as a probability without any causal explanation. Both Einstein and Schrödinger didn't agree with Born's way of explaining quantum mechanics. They believed in causality, which means everything happens for a reason. This was a key idea in science before quantum theory, and is still important in Einstein's theory of general relativity. In 1926, Einstein wrote a letter to Born saying, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he, God, is not playing at dice. He thought the theory didn't bring us any closer to understanding the universe's secrets. Einstein was sure that the universe wasn't just a game of chance. He famously said, "God does not play dice," meaning he believed there's a reason behind everything that happens in the universe. This shows his belief in a predictable universe, not one left to chance. In the beginning, even Heisenberg had intense disagreements with Bohr. He believed his matrix mechanics were not in line with Schrödinger's wave mechanics. Bohr was initially against Heisenberg's uncertainty principle as well. However, by the time of the Fifth Solvay Conference in October 1927, Heisenberg and Born felt that the quantum revolution was complete and nothing more was needed. This is when Einstein's skepticism turned into disappointment. He felt that while much had been achieved, the reasons behind the mechanics were still not understood. Einstein wanted to see a model that explained the underlying causes behind the seemingly random statistical methods of quantum mechanics. He didn't reject the idea that positions in spacetime could never be fully known, but he didn't want the uncertainty principle to force a seemingly random, non-deterministic way for the laws of physics to operate. Einstein, as a statistical thinker himself, believed that there was more to be discovered and clarified. He spent the rest of his life trying to find a new theory that would make sense of quantum mechanics and bring causality back into science. This is what many now call the theory of everything. Bohr, on the other hand, wasn't troubled by any of the things that bothered Einstein. He made peace with the contradictions by proposing the principle of complementarity, which assigns properties only as a result of measurements. This principle became a fundamental aspect of the Copenhagen interpretation of quantum mechanics. In the first stage of the quantum revolution, Albert Einstein was not ready to accept the inherent indeterminacy of quantum mechanics. He believed that there must be a way to accurately determine incompatible variables, such as position and velocity, and to reveal both the wave and particle aspects of the same process simultaneously. To prove his point, he proposed several thought experiments. One of these experiments involved a beam of light passing through two screens, each with slits. According to Einstein, by measuring the recoil of the first screen, S1, one could deduce which slit the particle passed through on the second screen, S2, without destroying the wave aspects of the process. If Einstein was correct, this would violate the principle of indeterminacy, which states that it's impossible to simultaneously measure certain pairs of variables, like position and momentum, with absolute precision. This thought experiment was first presented during the Fifth Solvay International Conference in 1927. Einstein's argument was based on the principles of separability and locality, not indeterminacy. Separability is the idea that objects separated in space can be considered distinct systems. Locality is the concept that an object can only be influenced by its immediate surroundings. Einstein believed that quantum mechanics, with its inherent randomness and spooky action at a distance, violated these principles. However, it's important to note that Einstein's thought experiments were not aimed at disproving the uncertainty principle. In fact, Paul Ehrenfest, a contemporary of Einstein and Bohr, wrote a letter to Bohr stating that Einstein had accepted the uncertainty principle and never doubted it. Niels Bohr initially misunderstood Albert Einstein's argument about the violation of relativistic causality, locality, by quantum mechanics. Instead, Bohr focused on the consistency of quantum indeterminacy. To illustrate Einstein's idea more clearly, Bohr proposed a thought experiment involving a screen that could slide up or down along a rod. Bohr argued that to determine through which slit a particle passed, one would need extremely precise knowledge of the vertical motion of the screen. However, according to the principle of indeterminacy, a precise determination of the velocity of the screen would inevitably lead to an imprecision of its position. This would affect the interference pattern on the final screen, making it uniformly gray. Thus, any attempt to evidence the particle-like aspects of light at the slits would destroy the possibility of interference, which depends crucially on the wave aspects. Bohr's argument hinged on the fact that a macroscopic system, in this case the screen, obeys quantum laws. He consistently held that to illustrate the microscopic aspects of reality, it is necessary to set off a process of amplification, which involves macroscopic apparatuses that obey classical laws and can be described in classical terms. This ambiguity would later resurface as the measurement problem in quantum mechanics. In quantum mechanics, we often talk about the uncertainty between position and momentum, also known as the Heisenberg uncertainty principle. Simply put, it states that it is impossible to simultaneously know both the exact position and exact momentum, which includes velocity and direction of a particle. In other words, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. There is also another important uncertainty relationship, that is, between time and energy. The time-energy uncertainty principle is another aspect of Heisenberg's uncertainty principle. It states that the more precisely the energy of a system is known, the less precisely we can know the time duration over which it remains in that energy state, and vice versa. This means that for very short periods of time, there can be significant fluctuations in energy, which allows for the temporary creation of particles from nothing, as long as they disappear quickly enough. For better understanding, imagine an experiment where a wave, limited in space, is sent through a slit that's only open for a very short time. This wave isn't just one frequency, like a pure musical note, but a mix of different frequencies. This mix creates a wave packet, which is a region where the wave is not zero. The wave packet moves over time, and its shape comes from the constructive interference of the different frequencies. But as you move away from this region, the different frequencies start to cancel each other out. If the wave packet has a spatial extent of delta x, which means the slit was open for a time, delta t equals delta x divided by v, where v is the wave speed, then the wave contains frequencies within an interval delta nu that satisfies the relation delta nu is greater than or equal to 1 divided by delta t. Now remember that energy and frequency are related by Planck's relation E equals h times nu. So the particle associated with the wave has an energy that's not perfectly defined, leading to an uncertainty in energy. Delta E equals h times delta nu is greater than or equal to h divided by delta t. This leads us to the uncertainty relation between time and energy. Delta E times delta t is greater than or equal to h bar, which says that the more precisely you try to measure the energy of a system, the less precisely you can know the time, and vice versa. This is a fundamental aspect of the quantum world. Einstein was not satisfied with the indeterminacy of the relationship between time and energy. So, at the 1930 Solvay conference, he proposed a thought experiment involving a box known as Einstein's Box containing electromagnetic radiation and a clock. The clock controls the opening of a shutter, which covers a hole in the box. When the shutter opens, a photon escapes from the box, creating a wave of limited spatial extension. Einstein argued that by weighing the box before and after the photon escapes, one could determine the energy of the photon with high precision. This would violate the uncertainty principle between time and energy. Einstein's idea was to challenge the indeterminate relationship between time and energy. He proposed that by weighing the box before and after the photon escapes, one could determine the energy of the photon with high precision. This is because the energy of the photon is equivalent to the mass it carries away from the box, according to Einstein's mass-energy equivalence principle, E equals mc squared. The clock would provide the precise time of the photon's emission. If Einstein was correct, this would mean that the product of the uncertainties in energy and time could be made smaller than what is implied by the uncertainty principle, contradicting the foundations of quantum mechanics. This argument seemed unassailable and sent shockwaves through the scientific community. Niels Bohr was particularly affected. According to physicist Leon Rosenfeld, it was a real shock for Bohr, who at first could not think of a solution. For the entire evening, he was extremely agitated, and he continued passing from one scientist to another, seeking to persuade them that it could not be the case, and that it would have been the end of physics if Einstein were right, but he couldn't come up with any way to resolve the paradox. I will never forget the image of the two antagonists as they left the club. Einstein, with his tall and commanding figure, who walked tranquilly with a mildly ironic smile, and Bohr, who trotted along beside him, full of excitement. The morning after saw the triumph of Bohr. Niels Bohr found a way to counter this argument by appealing to one of Einstein's own great ideas, the principle of equivalence between gravitational mass and inertial mass, along with the time dilation of special relativity, and a consequence of these, the gravitational redshift. Bohr argued that for Einstein's experiment to work, the box would have to be suspended on a spring in the middle of a gravitational field. After the release of a photon, a mass could be added to the box to restore it to its original position, allowing us to determine the energy lost when the photon left. However, the box is immersed in a gravitational field of strength g, and the gravitational redshift affects the speed of the clock, yielding uncertainty in the time required for the pointer to return to its original position. Let's denote the uncertainty in the mass by delta m and the error in the position of the pointer by delta x. Adding the load to the box imparts a momentum that we can measure with an accuracy of delta p, where delta p is approximately equal to delta m times v. Clearly, the uncertainty in position times the uncertainty in momentum is greater than or equal to Planck's constant divided by 2 pi. By the redshift formula, the uncertainty in the time is delta t, and the uncertainty in energy times the uncertainty in time is greater than or equal to Planck's constant divided by 2 pi. We have therefore proven the claimed uncertainty relation. Bohr's triumph was not just in demonstrating that Einstein's argument was not conclusive, but also in the way he arrived at this conclusion by appealing to Einstein's own principles. This highlights the intellectual rigor and depth of the debates between these two giants of physics. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" This paper, known as the Epr Paper, presented an argument based on the entangled state of two systems. Before presenting the argument, they formulated a hypothesis based on Einstein's work in relativity, the principle of locality. This principle states that elements of physical reality that are objectively possessed cannot be influenced instantaneously at a distance. David Bohm, in his 1951 textbook Quantum Theory, revisited the EPR argument and reformulated it using the concept of entangled particles. Here's a simplified summary. Imagine two photons at different locations, A and B, that are entangled, meaning their states are linked. They're in a specific state of polarization, which can be represented as a combination of vertical V and horizontal H polarizations. At a certain time, the photon at location A is measured for vertical polarization. If it passes the test, the system's state changes to both photons being vertically polarized. Now, the observer at A, who hasn't done anything to disturb the system or the other photon, can predict with certainty that the photon at B will also pass a test of vertical polarization. This means photon B has a real physical property, vertical polarization. According to the principle of locality, the action at A couldn't have created this property for photon B. So we must conclude that photon B had this property independently of the measurement at A. The observer at A could have chosen to test for a different polarization angle, say 45 degrees. Depending on the result, they could conclude that photon B is polarized at either 45 degrees or 135 degrees. But combining this with the conclusion from locality, it seems that photon B, before any measurement, had the property of passing both a vertical polarization test and a 45 degrees or 135 degree test. These properties are incompatible, according to quantum mechanics. So we're forced to conclude that photon B simultaneously possesses incompatible properties. Even if we can't determine these properties at the same time with perfect precision, they are objectively real. But quantum mechanics denies this possibility, suggesting that it's an incomplete theory. Bohr's response to the EPR argument was published 5 months later in the same journal, Physical Review, and even bore the same title. Bohr's key point was a critique of the EPR's assumptions. Bohr states, "The statement of the criterion in question is ambiguous with regard to the expression without disturbing the system in any way." Naturally, in this case, no mechanical disturbance of the system under examination can take place in the crucial stage of the measurement process. But even in this stage, there arises the essential problem of an influence on the precise conditions that define the possible types of prediction that regard the subsequent behavior of the system. Their arguments do not justify their conclusion that the quantum description turns out to be essentially incomplete. This description can be characterized as a rational use of the possibilities of an unambiguous interpretation of the process of measurement, compatible with the finite and uncontrollable interaction between the object and the instrument of measurement in the context of quantum theory. Rosenfeld, a close associate of Bohr, later provided a more accessible explanation. He states, "In the case of the two particles, it is true that the measurement carried out on the first particle does not cause any direct physical disturbance of the second, but the measurement decisively affects the nature of verifiable predictions we will be able to make about this second particle. As long as we do not carry out any measurements, we have no control at all over this correlation between the two particles. If we really want the system to be subject to study and communication, we must carry out some measurement. If we now observe the position of the first particle, the correlation between the positions of the particles can be used to give us information about where the second particle is, but we have no way of making use of the correlation between the pulses of the particles. If we observe the momentum of the first particle, it is just the opposite. We retain control over the momentum correlation, but lose it over the position correlation. The two different measurements define two complementary phenomena that can never be reconciled into a single description of the given two-particle system." After Einstein proposed his EPR experiment, many physicists conducted their own experiments to test his idea of spooky action at a distance. The first definitive proof came in 1949 when physicists Qianxiong Wu and Irving Shaknov demonstrated this theory using photons. In 1975, Alain Aspect proposed an experiment to test the non-separability of quantum mechanics. This led Aspect and his team, including Gérard Roget, Jean Dalibard, and Philippe Grangier, to conduct several complex experiments between 1980 and 1982 that further established quantum entanglement. In 1998, a significant experiment was conducted in Geneva. Two detectors were set 30 kilometers apart, virtually across the entire city, using the Swiss optical fiber telecommunication network. This distance allowed for the angles of the polarizers to be commuted. The two distant polarizers were entirely independent, and the measurements were recorded on each side and compared after each experiment using an atomic clock. This experiment verified entanglement under the strictest and most ideal conditions possible. If Aspect's experiment suggested that a hypothetical coordination signal traveled twice as fast as the speed of light, c, the Geneva experiment reached 10 million times c. This series of experiments played a crucial role in establishing the validity of quantum entanglement, a key principle of quantum mechanics. In the final stage of his life, Einstein further clarified his views on quantum theory. He was deeply troubled by the theory's complete abandonment of all minimal standards of realism, even at the microscopic level. From the early days of quantum theory, Einstein's thinking was guided by the assumptions of locality and Lorentz invariance. This led him to believe that if we demand strict locality, then hidden variables naturally follow, as suggested by the EPR argument. Bell, building on this EPR logic, showed that local hidden variables imply a conflict with experimental results. What was ultimately at stake for Einstein was the assumption that physical reality is universally local. While the majority of experts in the field agree that Einstein was wrong, our current understanding of quantum mechanics is still not complete. In reflecting on the Bohr-Einstein debates and the relentless pursuit of understanding the universe, we are reminded of Einstein's own words. The important thing is not to stop questioning. Curiosity has its own reason for existing. This spirit of inquiry and the enduring quest for knowledge continue to inspire scientists and thinkers across generations. As Richard Feynman once said, "I would rather have questions that can't be answered than answers that can't be questioned."